Section 2.2, the neuron and neuronal signaling. Establishment of a membrane potential. So far, we've only talked about the existence of this membrane potential. The resting membrane potential being a negative number, anywhere between minus 100 to minus 50 millivolts, depending on the cell type. But we have not talked about how the membrane potential is actually established. The membrane potential is established from the movement of a minute amount of inorganic ions across the cell membrane. So inorganic ions would be sodium, potassium, Cl-, calcium, magnesium. This small displacement of ions practically leaves concentrations across a membrane unaffected. So again, going back to what I said earlier, the concentrations of these ions across the cell membrane are not going to change. Okay, we do not have to worry about those gradients, those concentration gradients, those chemical gradients changing over time. The slight discrepancy in plus charge and thus minus charge across the membrane leads to these ions lining up at the membrane across from each other. So in part 1 right here, or this picture right here, we have an exact balance of charges on each side of the membrane, and the membrane potential is 0. So you have equal amounts of positive and minus charge on both sides. Now, in this side, what we have is just a few plus charges being moved in one direction. And you can see that the plus and the negative charges right at the membrane are sort of lining up across from each other. Why? Because you have a discrepancy in charge. You have a little bit more positive charge on the left-hand side, a little bit more negative charge on the right-hand side, because you moved positive charge from the right-hand side to the left-hand side. So now they're going to line up at the membrane because the system wants to go back to neutrality, but the membrane is getting in the way. So it sort of works as a capacitor. You can think of it as a capacitor. This is how a membrane potential is established. Note that overall concentration of these ions are unaffected, yet their local concentrations are affected. In cell biology, there are many instances where overall concentration of a molecule is unchanged, while local concentrations at some part of the cell is dramatically increased or decreased. So here, you can see that local concentrations of positive charge have increased. When we're looking at the picture with the green box around it, local concentrations of positive charge have increased on the left-hand side, while local concentration of negative charge has increased on the right-hand side of the membrane. Whereas overall, elsewhere, like here and here, not much has changed, right? So it's just a small change in local concentrations of positive and negative charge across the membrane. How is the membrane potential for minus 70 millivolts established? Well, you have the sodium-potassium pump, which moves 3 sodiums out of the cell while moving 2 potassiums in per cycle. The actions of this pump establishes the sodium and potassium gradient across the cell membrane. It is also electrogenic since it is pumping 3 plus charges out, bringing 2 plus charges in for a net of 1 plus charge out. Okay? On all mammalian cell membrane, there exists a potassium channel which is always open, called the potassium leak channel. So this is a channel that's always open, and what this channel will do is will make the cell membrane slightly permeable to potassium. So what we're going to do next is find out, okay, if the membrane is slightly permeable to potassium, what will potassium do? Which direction will potassium flow? Because remember, making the cell permeable with a channel will only allow the ion that channel conducts to move down its electrochemical gradient. So which direction is the electrochemical for potassium pointing? Is it pointing out of the cell or pointing into the cell? Remembering there's more plus charge outside the cell than inside, because when you're at minus 70, you're negative inside, positive outside. A higher concentration of potassium inside the cell than outside the cell, which results in the electrochemical gradient for potassium pointing slightly out of the cell. So we have a few things. Let's just draw this out, right? Here's my membrane, extracellular here, cytosol here. We're at resting membrane potential of minus 70 millivolts. we're slightly positive out, slightly negative in. So potassium, 140 millimolarity inside. And potassium concentrations and extracellular is going to be about 5 millimolarities. So the concentration gradient, or the chemical gradient for potassium is pointing out, chemical, and potassium is positively charged, so it would rather stay on the negative side, so its potential gradient is pointing in. That's all those words are saying. Now, I would recommend during this section, if you haven't already started doing this during this class, is to draw these things out. So everything that I said here can be drawn here the way I did it, and you will get a better picture of what's going on. Okay? So now we're just going to go ahead and calculate what is happening. At cellular concentrations of C outside 5 millimolarity and C inside 140 millimolarity, the equilibrium potential for potassium will be, and we just used that equation from before, we plug in the numbers, and we get an equilibrium potential of negative 89 millivolts. Now, negative 89 millivolts is not minus 70 millivolts, right? Which is the resting potential for the membrane, for the cell. So now what we're going to do is say, well, what does the concentration outside need to be if the equilibrium potential is minus 70? So we're going to plug in minus 70 for the V, for the voltage. We're going to put 140 in for the inside concentration, and we're going to solve for what does the concentration outside need to be. And when we do the math, we get to the concentration outside has to be 10.1 millimolarity. So for potassium to reach equilibrium, it needs to get to a concentration outside of 10.1 millimolarity, which does not equal to 5 millimolarity, which is the concentration of potassium outside the cell. So what this is telling us is that potassium's electrochemical gradient, let's go back up to our picture, its electrochemical gradient is pointing out. Okay, so electrochemical. Now, this arrow, maybe I should make it a little bit smaller because it's not a very strong electrochemical gradient. You can actually calculate that, but it is pointing out of the cell. So, since this membrane is permeable to potassium because of the potassium leak channels, constantly potassium is leaking out of the cell into the extracellular solution. But it is not allowed to reach equilibrium because the sodium-potassium pump is pumping potassium in constantly into the cell. So you have the situation where potassium is being pumped in, but it's also leaking out. Potassium is never allowed to reach equilibrium. Thus, potassium will diffuse out of the cell or out of cells through the potassium leak channels in an attempt to reach equilibrium. Another way to look at this, in order to establish the potassium equilibrium potential, plus charge needs to leave so that the membrane potential can go from minus 70 millivolts to minus 89 millivolts. The resting potential will always be higher than potassium's equilibrium potential. Potassium's equilibrium potential, at those concentrations, we did calculate it, and we got minus 89 millivolts, which is less than minus 70 millivolts being the resting potential. Depending on the cell types, if the resting potential is a little bit lower, potassium's equilibrium potential will be also lower than that. Okay? So potassium's electrochemical gradient when the cell's membrane is at the resting potential will always be pointing slightly out of the cell. This is always the case. Remember that, okay? But this is at resting potential. That is important to remember also. Therefore, a steady state is established where the amount of potassium entering the cell will equal the amount of potassium leaving the cell. Now, we have a new word here, steady state. right? And what does that mean? So I have an analogy that I came up with just a few days ago, and we're going to use that analogy. So a steady state, how do we explain this? So the analogy that we're going to use, so imagine that I have a water faucet, right? And I have a basin which has a drain. Here's my basin. And of course the drain goes down, loops back up, and goes out like that. Boom. Okay. And normally if I turn on the water, right, water comes out and water will go through here and exit that way, right? Now that is all fine and dandy. Now imagine that now I have some sort of debris slightly blocking the drain, okay? When I turn on the faucet, water does come through, of course, and it starts to build up, right? So I turn on the faucet, water is coming out, and it starts to build up. Initially, maybe it builds up to this level, right? And then I'm not changing the water pressure. A certain amount of water is coming out at a certain pressure. So this level will keep increasing until it reaches a certain level where water that is still going past the debris equals the water that is coming out of the faucet. So the level stays steady. Now, if I increase the water pressure a little bit more, what will happen is this water level will increase, but again, it'll reach a new state where the amount of water coming in equals the amount of water that's going out. So this is a steady state, meaning that nothing is changing. The level of water is not changing at the rates by which water is coming in this direction and the rate by which water is leaving through the drain. So a steady state is reached. Now, is this thing at thermodynamic equilibrium? No, it's not a thermodynamic equilibrium, correct? So thermodynamic equilibrium is a form of a steady state. But we use the word equilibrium in this class just for thermodynamic equilibrium because we want to differentiate between other steady states and thermodynamic equilibrium. Thermodynamic equilibrium is the point of maximum entropy for the system. I mean, when we look at the cell membrane and you have 140 millimolarities of potassium intracellular, 5 millimolarities outside, you're reaching a steady state at that point. Why? Because, let me scroll up a little bit. What is our steady state? I have my membrane extracellular and cytosol, right? And I have the sodium-potassium pump, right? What is the sodium-potassium pump doing? The sodium-potassium pump is bringing in 2 potassiums, taking out 3 sodiums, and of course using an ATP in the process. So sodium-potassium pump. Now, the other thing that I have on the membrane is this potassium leak channels. And the potassium leak channels, here's my potassium leak channels. All right. Now, the steady state that is established, and we're not really interested in sodium, we're more interested in this potassium that is coming in right here, right? Is that you have 140 millimolarities in and 5 millimolarities out. And as potassium is being brought in, a little bit of potassium is also leaving. So what will happen is if I have a system, okay, an artificial vesicle where I have a sodium potassium pump on it and I have leak channels, but I have, for example, 100 millimolarity of potassium on both sides, what will happen is the potassium pump will keep bringing in potassium, and eventually what you'll reach is this steady state, 5 millimolarity out and 140 millimolarity in. So the steady state is established because you have one system bringing in potassium and you have another system allowing it to leak out at a certain rate. And that leads to a steady state where this concentrations right here of intercellular and extracellular are not going to change. And that's the definition of a steady state. Now, a steady state can be easily shown mathematically, but the level of math required to do that is beyond the scope of this class. It's actually not that high level. It's just a junior level math class, differential equations, that easily lets you calculate these things. So this leads to a resting potential across a membrane where there is more positive charge outside than inside the cell. Now, the other thing that hasn't been mentioned is, okay, why are we just concentrating on positive charge? What's the deal with the negative charge? So you just have to remember that the negative charges are there in the cell, right? You have many molecules with full negative charges on them. For example, nucleotides, right? Nucleotide triphosphates, nucleotide diphosphates, nucleotide monophosphates all have these phosphate groups with negative charges. Proteins, they have a negatively charged C-terminus. And there's, of course, other molecules that have a full negative charge on them. So the negative charges exist within the cell. They're called resident negative charges. So the counter charges are, for example, all the other positive charges, including potassium. If you leave the negative charges alone and you move positive charge across the membrane, then you get an imbalance of charge, meaning that the negative charges are still there, but now you have removed positive charge. So you made the inside a little bit more negative because you don't have counter charges for those negative charges. So just remember that. That's why we're only talking about the movement of positive charge. So we have a thought exercise. Imagine lipid vesicles which only contain potassium channels which are initially closed. So we're going to have a membrane, right? We have the outside, inside. So here are my potassium channels. We'll just put one in for now. The inside contains potassium and Cl- at concentrations of 100 millimolarity each, and the outside contains sodium and Cl- at a concentration of 100 millimolarity each. So this potassium channel currently is closed, so we're just going to not do anything with it. So potassium, we're going to have potassium in green, so potassium concentration in green, 100 millimolarity, and Cl-, so Cl- we'll have it in red, 100 millimolarity, both outside and inside. And then we have sodium, and sodium, we'll have it in purple at 100 millimolarity. Okay, so obviously the charges balance out. Cl-, the red, is negative, and the two other ones are positive, so you have balance in charges across the membrane. But you can see that, okay, well, Cl-, there's no chemical gradient for Cl- in this case, but there's definitely a chemical gradient for sodium pointing directly in, and for potassium pointing directly out, because there's no potassium on the outside. So if I open this channel, which is a potassium channel, what will happen is potassium will flow out. So let's keep reading and then we'll go over it. The membrane potential will be 0. So currently it's 0 millivolts because you have equal amounts of both anions and cations on both sides, but sodium and potassium have concentration gradients pointing in opposite directions, potassium out of the vesicle and sodium into the vesicle. When potassium channels are open, potassium starts to diffuse out of the vesicle. So if I open this channel, potassium will start to diffuse out, right? It will start moving from inside to outside. This is also the movement of plus charge out of the vesicle, thus the outside solution starts to become positive and the inside negative. This leads to the creation of a potential in the membrane and an electrochemical gradient for potassium which counteracts its gradient, its concentration gradient. So as positive charge is moving from inside to out because this potassium channel is open, you're making the inside negative and the outside positive. And this number starts to become a negative number. So now the voltage will become some number x, negative x, right? Which is getting closer and closer to the equilibrium potential for potassium. If the system is allowed to keep going, it will eventually reach equilibrium, where this number x will be very close to the equilibrium potential for whatever concentrations are established across the membrane for potassium. Potassium will continue to diffuse until it reaches equilibrium. The potential on the membrane will be potassium's equilibrium potential. And potassium's equilibrium potential will, of course, be dependent on what the concentrations of potassium are when that equilibrium is reached. And by that, what I mean is potassium will keep leaking out, so the concentration of potassium on the outside part will start to increase. And eventually, the concentration gradient will equal to the potential gradient that is going to be established because of the membrane potential that is being established as positive charge is moving out. The resting potential establishes the electrochemical gradient for the other inorganic ions. At resting, so very important before we go on, at resting potential, at resting potential, at resting potential, at resting potential. So at resting potential, sodium's electrochemical gradient is pointing directly into the cell. At resting potential, calcium's electrochemical gradient is pointing directly into the cell. At resting potential, magnesium's electrochemical gradient is pointing directly into the cell. At resting potential, Cl-'s electrochemical gradient is close to equilibrium. So this is something that you probably calculated in the homework 3, that Cl-'s equilibrium potential is very close to the cell's resting potential. Okay? Now, for all of these other ones, you're like, I have to memorize all these, Dr. Sabahi? Well, yeah, you need to know these things, that at resting potential, which direction the electrochemical gradient is pointing. Or you can just remember what the concentrations for these are across the membrane, or have at least a really good idea of what they are, and then say, well, at resting potential, extra and cytosol, that I'm positive outside, negative inside, and when I look at sodium is about 145 outside, so sodium, 145 millimolarity outside, and 5 to 15 inside. Well, obviously, its concentration gradient, chemical gradient, is pointing in, and positive wants to go to negative, so its potential gradient is also pointing in. You add these up, you have a very strong electrochemical gradient pointing in. You can do that with the other ones too. For potassium, the chemical gradient is pointing out while the potential gradient is pointing in. For Cl-, the potential gradient is actually pointing out where the concentration gradient is pointing in. Calcium, etc. I always recommend start drawing things out to be able to see them instead of trying to memorize words. So the Nernst equation. The Nernst equation is just that equation that we learned in the first part of this section, which is how you get the equilibrium potential for any ion. So that's the name of the equation. Is a good tool for calculating equilibrium potential for a single ion. It fails when a number of ions need to be considered instead of just one. So across a membrane, you have these chemical gradients for sodium, calcium, magnesium 2+, and Cl-, and of course potassium, right? And the equilibrium potential for a single ion is important, but it's the contribution of all these ions, their electrochemical gradient, and the permeability of the membrane to these ions that leads to the resting potential that is established across the cell membrane. And the way to calculate that is to use this Goldman-Hodgkin-Katz equation, which factors in the contribution of all these ions to the cell's membrane potential. Now, we're going to take a look at it because this link will take you to this web page. And here's the web page. And we are going to not worry about any of this stuff And we have this equation. Vm being the membrane potential equals RT divided by F, a natural log of these numbers. Obviously, this is the concentration of potassium, sodium, and Cl- are being considered because these are the big ones that factor in the most to the membrane potential because they're at much higher concentrations than the other ones. Now, the P, for example, pK and pNa and pCl, it is a permeability value. Like pNa is the relative membrane permeability of sodium, pCl is the relative membrane permeability for Cl-, and etc., right? And that is a relative number. It's not a constant. It can change. And of course, concentration of potassium O means concentration of potassium outside. Concentration of sodium O is concentration of sodium outside, and etc. Now, when we start to use this equation to see what the membrane potential is, you start to get a better picture. So here we have a nice little web widget that you can put in stuff and get the number. So we're going to switch to millivolts here. So you can fill this with sample data, like right here. I just click that. Of course, the temperature is 310 because that's normal temperature. The permeability values we're going to leave alone, but what we're going to do is we're going to switch to the numbers that we have. So for potassium extracellular, we're going to go with 5. And we're going to go with 140. And sodium, 145. 15 is fine. We'll just go with a middle number, actually, 10. Because that's between 5 and 15. Cl- we have in our notes and our book 140. And inside we have 5 to 15, so 10 is fine. So we say calculate. So we're just trying to look for this Vm, what it gives us. So we say calculate, and you can see that, and this is in volts, we want millivolts, so calculate. You get minus 66.70, which is pretty close to minus 70, right? So with this thing, what you can do is kind of mess around with it. Now, it also, right here below, calculate the equilibrium potentials for potassium, sodium, Cl-, and this is just the equilibrium potential for this single ions. You can see that potassium's equilibrium potential is minus 89.01. This is the equation that you guys have been using, the Nernst equation that we just talked about. Sodium's is 71.43. And Cl- is minus 70.5, which is really close to the resting potential of the cell. Now, the thing that gets interesting, and I recommend that you guys come back to this and mess around with it, is that if we don't switch out, change anything with the concentrations, and we just mess around with the permeability. Remember, these are relative permeabilities. So the membrane is more permeable to potassium than it is to sodium and Cl-. You can see it's twice as more permeable to potassium than it is to Cl-. It's not very permeable to sodium. Now, of course, there's slight permeability to sodium because sodium is being brought in by all the sodium-driven co-transporters and etc. So sodium is coming in. So when we're talking about permeability of the membrane to a certain ion, we're talking about an average over a certain period of time. And the membrane is using sodium to drive these co-transporters. So what will happen if I keep the potassium's permeability and the Cl- permeability unchanged, but I increase this by 100-fold? So I put in 5 here, and I hit calculate. Now you can see that all of a sudden it's become positive. 28.47, right? If I go back, boom, we're back to minus 66. Now, what will happen if I make it very permeable, 10 times more, to potassium? It starts to become more negative. As you make the membrane more permeable to a certain ion, while not changing the permeability of the membrane to other ions, the potential on the membrane starts to move away from resting potential toward the potential, the equilibrium potential of that ion, right? So if I go back to 1, which is the normal permeability, I go back to minus 66. Now you can see that because the membrane is more at rest, it's more permeable to potassium and Cl-, the resting potential of the membrane is pulled toward the equilibrium potential of potassium and Cl-, which are minus 89.01 and minus 70.5. That's been calculated for you down here. Now, if I were, for example, make the membrane much more permeable, let's go with 100 here, to sodium, now I get very close. I start getting closer to sodium's equilibrium potential, which is sodium's equilibrium potential is 71.43, and the membrane potential is 66.51. Now, you might be asking yourself why you're doing this. This is why you're changing this. This doesn't happen. Well, we're about to discuss something where the membrane permeability to sodium and potassium will change to facilitate neuronal signaling. So come back to this and see what will happen. Now, what will happen if I drank a bunch of potassium chloride and increased the extracellular concentration of potassium? I made it spike. So let's say I put a 0 here. See? The resting potential goes up to minus 31, right? So, and let me just go ahead and plug that in again. And you can see that the equilibrium potential for potassium has gone to minus 27.5. So the contribution of potassium to the resting potential, which was pulling it down to a more negative number, is gone, and the resting potential has moved up because that contribution is not there. Okay? If we go back to 5, and we hit calculate, we go back to minus 66. Okay? So there's a couple of factors. The main one being the membrane's permeability to a certain ion. If it's very high, the membrane potential will start to move toward that membrane's equilibrium potential. And we saw that by increasing sodium's permeability by 100-fold, that all of a sudden the membrane potential spiked and went towards a positive number, towards sodium's equilibrium potential. Okay guys, we are going to stop here and continue with the neuron next. Thanks.